Okay. So, we have spent a considerable amount of time looking at logic and reasoning and theorem proving. One thing that was common in all of that was that you had to write programs which would search for matching formulas. So, for example, if you are doing backward chaining or forward chaining, then you have to search through the set of formulas for finding matching formulas which will allow you to do the chaining process. Now, obviously, search requires computational efforts. So, there has been a fair amount of work which is focused towards avoiding this search essentially, which means we are moving more towards representation now and trying to see ways of representation where this kind of reasoning would be much simpler essentially. Okay. So, one of the first ideas that came forward for this is the notion of semantic nets. And this idea is due to Ross Quillian. So, essentially a semantic net is a graphical form of representing of logic statements. So, you might have something like this. For example, you might say you are talking of Suresh and you might say that Suresh has a sister let us say who's called Sneha and Suresh has a wife, let us say she is called Janki, and then maybe Janki has a brother who is called let us say Rakesh, and so on and so forth. So, I have just shown some relations which are kind of human relationships, but any kind of a relation you could add. So, for example, you could say Rakesh lives in Chennai and Chennai is in let us say Tamil Nadu, and so on and so forth. So, you could have a whole network of such relations where every edge represents a relation and the every node is a term essentially, and you could sort of construct a whole thing. Now, what is the objective of this? The objective is that relations are, should I say, explicit. Well, they are even explicit when you talk about logic, but Charniak and McDermott use a term called concrete, in the sense that they are implemented, or if you want to call physical essentially or something. So, for example, if you wanted to ask a question as to who is Suresh's sister, then all you have to do is to follow the sister arc from Suresh and you get the answer. You do not have to search through any file looking for the sister relationship and then seeing whether one of the arguments matches Suresh and then returning the other argument and that kind of a thing. Quillen also gave some algorithms for working on them. We will not go into those, but I will just mention them here. So, these are algorithms which are known as marker passing, or also known as activation propagation. The idea here is that if you want to find some relation between any two entities. So, for example, if I were to ask is Suresh in any way related to Chennai essentially, then by spreading activation, okay, that is also a term that we use, spreading activation. By what do we mean? We in some sense we activate the nodes Suresh and Chennai, and then we spread the activation in the sense that we activate their connected nodes, and we keep doing that. So, this is also called marker passing sometime, because it is like you are marking those nodes and you are passing the marker to connected nodes till the point where the markers collide or when they intersect, then you know that you have found a path from Suresh to Chennai. In this case, you might give out the answer which says that Suresh's wife Janaki has a brother Rakesh who stays in Chennai essentially. So, this was one idea that was motivated by trying to avoid searching through unordered collections of formulas essentially. Of course, we saw that in Prolog they are not so unordered, because you really Prolog has a fixed search strategy, but the basic idea in logic is that somehow you will find a matching formula and then do the unification or matching and then make the inference essentially. A related idea, which is what we will pursue in the next couple of classes, is the idea of frames, and this is due to Marvin Minsky, who you must have heard of. He is one of the founding people in AI. He founded the AI lab in MIT, for example. And you can read up what we are going to discuss in this chapter 8 of Brackman and Levesque. So, I am basically going to teach from there the next couple of this class and so on essentially. So, the idea of frames was that the representation should reflect the domain structure or the structure in the domain essentially. So, just as domains that all the domains that we are interested in are structured, the knowledge representation should also reflect that structure essentially. And again the goal is to avoid searching for related elements. So, what do we mean by structure? We say that, so this corresponds to in some sense the structure that you use in a programming language, and this whole idea of object oriented programming actually came from this idea of frames, which says that your whatever you are representing should be a reflection of the domain that you are talking about. So, if you are writing about, for example, an institute, then you can your representation should say that okay, the institute, it has got departments and departments have people, and they have people could be staff members or they could be students and that kind of stuff. All this kind of thing is put together in one structure and stored essentially. And Brackman and Lewis, they talk of two kinds of frames. One is they call as generic, we can say abstract, and in some sense they correspond to what we think of as concepts. They are abstract essentially. I mean, they are not representing any specific thing or entity or something, but it is a concept. So, for example, what is a chair or what is a house, and those concepts are represented as generic frames essentially. And then we have instances of generic frames which are called individual frames. Which talk about specific entities, or you can say which correspond to objects. essentially. And one of the ideas that we will see is that frames allow you to do is, apart from the fact that you put everything together in one place, then other thing is that it allows for economy of representation, because you can represent things at a suitably abstract level and then inherit it into something which is more specific essentially. So, let us look at frames in a little bit more detail. So, frames are made up of a name and a collection of slot and filler structures essentially. So, the idea is so common nowadays that one does not need to elaborate it too much. So, we can represent it as follows. For example, okay, so first let me just write this. So, we have a name, then we have a slot and a filler. So, let us say slot I and filler I. And slot I plus 1, filler I plus 1, and so on essentially. So, some kind of a structure, and there are two special slots. One is, and this is in the terminology of Brackman and Levesque, one is called is a slot and the other is called instance of. So, these are two special slots. So, you can think of a slot as property and a filler as value. So, remember the triples notation that we talked about when we were talking about RDF. So, subject, predicate, object, or subject, property, value essentially. So, the subject here of course, is a name, that whatever is the concept you are talking about, and then there is a whole set of property values that you put together into one physical location in some sense and keep it together essentially. So, that is the whole idea of avoiding search essentially. Now, this value can be another frame. So, then you can see that this whole idea of which was we talked about in the semantic network or semantic net is also being incorporated here, because you essentially have these nodes which are frames and they are linked to other nodes through all kinds of relations essentially. So, these slots, they capture the relations or the edges in the semantic net, you might see essentially, in case you put in a pointer there. Now, these slots can have attached procedures and typically these procedures might be as follows. So, for example, there might be a procedure which is of the kind if added, and it specifies that if filler is added, then do something. some if some code has to be run, then as soon as you fill in a value, uh, you execute a procedure to do something essentially. So, for example, you might say okay, create another frame with this name and this data. We will see some idea a little bit later, and the other thing can be if needed. This says that if you need the filler, then run this procedure. Again, we will see in an example that maybe you have constructed some frames, and then at the end of it you want to do some computation, and that computation, for example, could be a value or something, and this if needed procedures would be used to compute those values essentially. Now, you can associate this if added procedures with eager reasoning, and we have discussed these concepts earlier. We also call it forward chaining. And this if needed likewise can be lazy or backward. Okay. Now, by and large, the most important thing that we get out of frames, the idea that we get is that of inheritance. So, let me illustrate this with a small example. So, let us say we define a frame called elephant. So, Blackman and Levesque say that capitalized names stand for generic frames. This is just a convention that we follow, just as Prolog says that capital are used for variables and lowercase is used for constants. So, elephant is a generic frame, that means it is a concept of an elephant that we are talking about. Then it might have some of these special slots. So, for example, is a, and this could be a pointer to another frame whose name is mammal. So, which we will not fill, but essentially we can say that an elephant is a mammal essentially, and we can specify some things for elephants. So, whenever we say that an elephant is a mammal, we are essentially saying that is a type of essentially. So, it is a subclass of in some sense or the subconcept of or subcategory of essentially. Now, in inheritance you can say that how many some property. So, let us say eyes and let us say 2. Okay. So, let us say essentially trying to say that mammals have 2 eyes essentially. Then the whole idea of inheritance is that once you do that, once you create an elephant frame and say that it is a type of a mammal. So, this is inherited here. You do not have to represent the fact that elephants have 2 eyes or leopards have 2 eyes or cats have 2 eyes and so on and so forth. As long as you say that they are mammals, whatever is true of mammals will apply to them essentially. Then you could have another frame which says it is a royal elephant, and here I could say is a. So, I am writing it here, but you can think of this as a pointer, it does not matter. I mean I just said elephant, but it's basically a pointer to the elephant frame essentially. So, you need to distinguish between pointers and literals, and there must be some mechanism to do that essentially. So, I might have said in elephant one of the properties is that the color is gray. Now, one would expect that this property, that elephants are gray, would be inherited by royal elephants, but frame systems allow you to override such properties. So, you could say color white. So, you could think of this as default, and overridden by this value. And then I could have another frame. So, this is a individual frame, because I have used this lowercase letter, and I could have this instance of and so on and so on. So, what do I know about Clyde? We know that Clyde is a royal elephant, we know that Clyde is an elephant. We will also infer that Clyde is white in color and not gray, because in the frame system that you are talking about, you can override the default. And we can say that Clyde has 2 eyes and all that stuff you can get from inheritance essentially. One can inherit from multiple sources, that is allowed, it does not have to be only one parent. So, for example, I could have said that royal elephant is an let us say African animal. An African animal could be a concept which talks about all those animals that are found in Africa, and African animals could have certain properties which are different. Which would be inherited also by the royal elephant. So, royal elephant inherits properties from here as well as from African element essentially. So, one might ask, what if we are trying to inherit 2 different properties from 2 different ancestors essentially. Now, that is a tricky question which we will defer for the moment, and we will try to see that if you have to decide based simply on the topology of the graph that you are constructing as to what is the right thing to inherit, then that is a question which needs some thought essentially. We will defer it to later, but as of now frame systems do not allow, I mean they do not allow, they do not restrict you. So, say they do not check for consistency essentially. So, for example, if I had said that the royal elephant is a fish, nothing in this whole system would crop up to say that no, there is something wrong with that, fishes are not elephants and that kind of stuff. We will look at something called description logics maybe next week sometime, in which we will be able to spot such difficulties essentially. So, I am kind of rushing through this and I would expect you to read this chapter 8 from Brackman and Levesque, where the example that I am going to talking about is discussed in more detail. So, I just want to illustrate as to what is the idea behind this kind of a frame structure essentially. Okay. So, the basic idea is that generic frames contain knowledge and they are used to create individual frames. So, you can think of this short description that I will give you and which is also given in the book as something like a personal travel agent, that you have implemented a system where if you want to let us say plan a trip, you want to go to a couple of cities and come back, then you start invoking this system and the system kind of helps you along essentially. So, the basic idea is something like this, it's like a kind of a structured spreadsheet or like a see a normal something Excel that you use normally is a flat structure where you relate some cells to other cells and so on. But here we are talking about a more structured knowledge representation, where you have types of things and you have taxonomies and things like that, and you can sort of store all this knowledge that you want to talk about in a compact fashion essentially. So, when we are talking about trips, then let us say we have something called a trip, one generic frame called a trip, and then there are other generic frames like travel part, and lodging, stay and so on. So, these are generic, and this generic frames will be used to instantiate individual frames essentially. So, let us say I am planning a trip, I want to go to a couple of cities. So, I will invoke this system, that frame system that I have built, and I will say something like let us say trip 27. I want to create a trip. So, I am using lowercase here because it is an individual frame. So, let us say my trip number 27, and let us say it is a 27th trip essentially. So, the moment I say I want to create a trip 27, so I will start off by saying that it is a it is an instance of trip, and the moment I say this, the system should create first leg and point it to another individual frame which says travel something like 27 first leg or something like that essentially. And it should prompt me for date, start date, destination, and let us say I am just giving a few things, next step essentially or next leg. So, the system should prompt me, okay, you want to go on this trip, what is this value, what is the destination and what is going to be the next leg essentially. So, let us say I fill in some date, let us say 27th March and let us say Delhi, and let us say I say next leg is Chandigarh. The moment I fill in these 3 steps, so maybe it will ask me when is the next date also. And let us say I say 29th. The moment I have provided this information, the system should create a lodging step lower case of trip 27(1), and it should say let us say it is figured out that I am going to travel by air. So, the lodging stay should begin on 27th March and it should end on 29th March and so on and so forth essentially. So, this is a basic idea that in the generic frames you know, for example, you can store information like how do you normally pay for your travel, whether you pay by credit card or whether you have a travel agent who gives you credit, and which airline do you normally prefer or which hotel do you prefer. So, if I say I am going to Delhi, then maybe the system will know that I stay in a particular hotel, and so it should try to fill in all that kind of stuff here and essentially help me plan my whole trips. So, it should know that, for example, there should be a return leg. So, it should remind me that okay, you can't get stranded, what is the last leg. So, it should automatically create a return leg, and at that point it should stop creating lodging stays and things like that. It should look at this, say, so for example, if I am going to Chandigarh in the morning and leaving in the evening, maybe it will not create a lodging stay. All this kind of stuff can be put in by if added and if needed procedures that we have just spoken about essentially. Okay, so, I will not go into the details because it is a very descriptive kind of a thing. I will expect you to read this chapter 8 where this is described in considerable detail essentially. In the next class, I want to move over to another application of frames which was used in natural language processing, which is also tied up to our study of conceptual dependencies. So, this is the idea which came from a different school, which is this idea of scripts, and we will look at it in the next class.